Good day, everyone. I am Dominique Ybañez, and on behalf of our research team, allow me to present our undergraduate thesis entitled A Systematic Review of Biosensors Suitable for Environmental Biomonitoring of Heavy Metal Water Pollution in the Philippines. Heavy metals present in different bodies of water may impose both environmental and health risks, especially since water is essential to everyday living. This type of pollution commonly originates from industrial wastes like mine tailings, smelting, and insecticide use. According to Magalona et al., chronic exposure to heavy metals have been reported in the Philippines, specifically in Central Luzon. It was identified that there was an increased level of arsenic in both tap and groundwater sources used in nearby households. The 2008 Water Quality Monitoring Manual of the EMB DNR lists arsenic, nickel, cadmium, mercury, chromium, copper, and lead as the heavy metals which require monitoring due to their toxicity and prevalence. DNR also has a project named Water Quality Monitoring Program, which includes the detection and monitoring of heavy metals in different bodies of water. However, the use of heavy metal biosensors are not included. These are some examples of the current methods of heavy metal detection in the country. So what are biosensors? These are devices used to detect the presence of chemicals or analytes for reaction detection through the generation of signal in proportion to the concentration of the analyte. They are characterized by their high sensitivity and selectivity. As stated previously, the Philippines is dependent on conventional detection methods. Our review focused on the proposal of a suitable environmental biosensor model for heavy metal detection in the bodies of water in the Philippines, based on a comprehensive review of existing literature and research on environmental biosensors. The study included three components of a biosensor: the transducer type, transduction method, and bioreceptor, as these three components affect the sensitivity and selectivity of the biosensor model. The heavy metals our research focused on are arsenic, copper, cadmium, lead, and mercury. The main aim of the systematic review is to determine the most suitable biosensor model for environmental waste management with respect to heavy metals in the Philippines. To meet this objective, we have set specific objectives wherein we conducted a systematic review with the use of published research papers on environmental biosensors. And through this, we identified the transducers, transduction methods, and bioreceptor types of these biosensors, and we proposed a biosensor model based on their limit of detection, or LOD, and selectivity. The research focused on published biosensor models for environmental monitoring of freshwater pollution. Furthermore, only articles published in databases of the NCBI, PubMed, PLOS One, and Science Direct were chosen. We only concentrated on arsenic, cadmium, copper, lead, and mercury in the Philippines because of the literature and reports we have gathered. These are the heavy metals that are the most prevalent in the bodies of water and considered as health concerns. Lastly, the researchers aim to propose a biosensor based on their LOD values, selectivity performance, and the number of bodies of water the biosensors can be used. We chose these factors because they are the components of the biosensors used by researchers in evaluating their performance. For the methodology, two search strategies were conducted. First was following the guidelines published by PRISMA in the databases of NCBI, PubMed, PLOS One, and Science Direct. Second, 13 search keywords were utilized and the Boolean search operator AND was used. To further refine the journal articles that will be included in the study, an eligibility criteria was followed. They are considered eligible if they are a peer-reviewed primary research article that was published in English. They must discuss biosensors, environmental monitoring, and heavy metal pollution. Information about the biosensors listed in this slide must be stated in the study. These are the specific pieces of information the researchers look for in the journal articles. The Joanna Briggs Institute, or JBI appraisal checklist, was used for the quality evaluation of the journal articles. The questions in the checklist were answerable with yes, no, unclear, and not applicable. The researchers will decide whether to include, exclude, or seek further information about the journal articles. A total of 57 journal articles were included in the study. The 3 biosensor components, LOD, and interfering ions were collected from them. The data was analyzed by tabularizing them in the Microsoft Excel sheet with column headings of the analyte, authors and years, transducers, transduction methods, specific bioreceptors, LOD, which are converted into ppm, and interfering ions. The LOD values were converted for the sake of uniformity and easy comparison. The suitable biosensor was proposed based on their selectivity, manifested in their LOD, the number of applicable bodies of water in the Philippines the biosensors can be used, and lastly, their selectivity based on the number of interfering ions tested during the biosensor development. The summary is presented in the figure, which is a PRISMA flow diagram of the journal article screening. A total of 317 articles were retrieved from the 4 databases, which then went through the removal of duplicates and checking for the eligibility criteria. Only 57 journal articles were included, where 5 of these were for arsenic, 6 for copper, 10 for cadmium, 13 for lead, and 23 for mercury. For the critical appraisal using the JBI checklist, all 57 journal articles fortunately passed the evaluation. The limit of detection values stated in each chosen journal article were taken, and these were used along with the data of the different concentration levels of the 5 heavy metals reported in the bodies of water in the Philippines. The selectivity criterion is based on the detection of the analyte when there are interfering ions present. In this review, the selectivity was evaluated based on the capacity to recognize the analyte among the 12 common heavy metal pollutants in the Philippines: lead, copper, nickel, cadmium, chromium, zinc, manganese, titanium, aluminum, iron, mercury, and arsenic. Lastly, the number of applicable water sources refers to the number of contaminated locations in the Philippines as reported, where the biosensors can be used for environmental biomonitoring. This was conducted using the sensitivity criterion, or the LOD values, the biosensors, and it has to be lower than the concentration levels recorded in the polluted area. The optical biosensor of Du et al. Has the lowest LOD, hence it has the highest sensitivity. For the second criterion, the optical biosensor of Fu et al. Had the best selectivity because it can detect lead in the presence of 9 interfering ions. For the last criterion, 4 biosensors composed of 3 optical and 1 electrochemical are suggested because they can be used in all identified lead-polluted water sources. To further refine the selection, Fu et al. Was eliminated on the basis of its low sensitivity and applicability for sensing the water sources. Thus, only 4 biosensors were left for further analysis. In the next round of the elimination process, we had to factor in the selectivity of the remaining biosensors. He et al. And Zhang et al. Had the highest number of interfering ions. Thus, the only 2 were selected for the final analysis. The 2 remaining biosensors can identify lead in the presence of 5 interfering ions and are applicable in monitoring all of the lead-contaminated bodies of water. Hence, we had to evaluate them again, this time using their sensitivities, which resulted to suggesting the optical biosensor of He et al. Because of its LOD of 3.6 times 10 raised to negative 8 parts per million. So just like in the prior slides, we first identified which biosensor had the lowest LOD. In this case, the electrochemical biosensor of Tang et al. For selectivity, 4 optical biosensors were able to detect mercury in the presence of 9 interfering ions. For the number of water bodies the biosensors can be used, 12 biosensors composed of 8 optical biosensors and 4 electrochemical biosensors are suggested. For the final assessment, 10 biosensors were removed because their selectivities were smaller compared to the biosensors of Han et al. And Tang et al. The selectivity was used for the assessment. And this resulted in proposing that Han et al. Is the most suitable mercury biosensor because it had the highest interfering ions. The electrochemical biosensor of Yadav et al. Had the lowest LOD, while the optical biosensor of Pan et al. Had the best design for selectivity because it can detect 7 interfering ions. 2 optical biosensors and 2 electrochemical biosensors are applicable to all of the identified arsenic polluted water sources in the Philippines. Upon further evaluation, the selectivity criterion will determine which arsenic biosensor is truly suitable. The optical biosensor of Pan et al. Can detect arsenic in the presence of 7 interfering ions. Even though the LOD of Pan et al. Is higher compared to Yadav et al., we still opted to suggest it because of its quality in terms of its selectivity. The optical biosensor of CAR and Burma had the lowest LOD, which means it has the highest sensitivity. For selectivity, the optical biosensor of Zong et al. Can detect copper with the most number of interfering ions. The optical biosensor of CAR and Burma, Ren et al. And Su et al. Were found to be suitable for all of the concentration levels for the copper-contaminated bodies of water. In the overall assessment, the optical biosensor by Ran et al. 2018 was suggested for copper detection because its LOD value is still good as it fits the concentration levels and it can detect copper in the presence of 8 interfering ions. Zong et al. Had good selectivity but low sensitivity. On the other hand, Carr and Verma or Su et al. Were eliminated because of their selectivities. The electrochemical biosensor of Ibrahimi et al. Had the highest sensitivity. The optical biosensor of Elsin and Octem was selected because of its selectivity as it can detect cadmium in the presence of 8 interfering ions. Based on the most covered water sources, we have the optical biosensor of Luan et al. And the electrochemical biosensors of Li et al., Ibrahim et al., and Wei et al. But for our overall assessment, we ended up with the optical biosensor of Zhu et al. And Zhao et al. This is because their LOD values still fit most of the bodies of water in comparison to other candidate biosensors, while having a good selectivity performance of 7 interfering ions, following the highest value of 8 interfering ions of Elsin and Octem. In comparison to the biosensor of Ibrahimi et al. And Elsin and Octem, it performs well for both sensitivity and selectivity. The proposed biosensors in this study were all analyte-specific. In other words, are only intended for one type of heavy metal. However, there were already reports of multi-analyte biosensors in other countries like that of Zhang et al. And Gu et al., which were used for lead and cadmium. Their biosensors showed real-time monitoring in remote locations and a good limit of detection values. Additionally, in 2015, Lu et al. Was able to incorporate an unmanned aerial vehicle or drones for air quality control and water pollution monitoring. Future systems based on the fusion of biosensors and drones would be desirable for the environmental monitoring in remote locations due to their low cost, compactness, and low power requirements. With these characteristics of biosensors and the findings of this review, an all-in-one or multi-analyte biosensor may be developed. So for the summary, heavy metal water pollution has been reported in the Philippines. The methods of the DENR in monitoring these heavy metals do not include the use of environmental biosensors. Hence, a systematic review was conducted to propose an appropriate biosensor for the heavy metal detection. 4 databases, NCBI, PubMed, PLOS One, and Science Direct were searched for the necessary articles. 3 assessment points were followed by the researchers. These are the sensitivity in the form of LOD, their selectivity, which is based on the interfering ions, and the number of bodies of water the biosensors can be utilized, which is based on the sensitivities. So optical biosensors are most considered for copper and lead, while electrochemical biosensors are optimal for arsenic, cadmium, and mercury. As for selectivity, optical biosensors are most suitable for all the heavy metals. The proposed biosensors are applicable in all of the identified polluted water bodies in the Philippines. but they can also be utilized outside of the country if only their concentration levels are within the detectable range of the biosensor. The researchers concluded that optical biosensors are most suitable in the detection of lead, mercury, arsenic, copper, and cadmium. This study can be considered as a basis on heavy metal water pollution research and biosensor development. Lastly, despite the analyte-specific characteristics of the proposed biosensors in this study, a multi-analyte biosensor has been developed, and the possibility of designing a biosensor that can detect all 5 or even more analytes may be possible. It is recommended in the future studies that they may focus on the proposal of a biosensor based on the comparison of the biosensor components. They design a bioreceptor that has the capacity to attract different metals. Additional biosensor characteristics such as signal amplification, response time, and selectivity values may be included for the data analysis. And lastly, the use of different bioinformatics strategies such as regression, artificial intelligence, and machine learning techniques may be used to predict the suitable biosensor and for data analysis. So this concludes my presentation. Thank you very much for listening and have a nice day.